Afternoon students, welcome back to chemistry class. Today we are going to study about how the atomic radius or covalent radius vary in group. Okay, yesterday we studied about that how the atomic radius vary in periods. Okay, and today we are going to study about how the atomic radius vary in group and ionic radius, and about ionic radius and how to calculate the ionic radius. That all today we are going to learn. Okay, before that, last class I given one of the homework. Using Slater's rule, calculate the effective nuclear charge on a 3p electron in aluminum and chlorine. I don't know how many of you written this, practiced this homework, but once again I will explain the Slater's rule with this example. Okay, so use Slater's rule, calculate the effective nuclear charge on a 3p electron in aluminum and chlorine. Okay, so aluminum, what is the atomic number? 13. Electronic configuration 1s2, 2s2, 2p6, 3s2, 3p1. Okay, 1s2, 2s2, 2p6, 3s2, 3p1. According to Slater's rule, what is the first rule? First rule, which one is the first rule? We should write the electronic configuration of a particular atom. What is the second step? We should arrange this electronic configuration in group. Okay, which group? According to K shell. K shell means what is the subshell? Only one subshell. L means L shell is N is equal to 2. L is the second shell. What are the subshell? S and P. Okay, this S and P orbital we grouped together. S and P orbital we grouped it together. Others separate. Okay, and now we are going to grouping this electronic configuration. First 1s2, 2 electron, and the second 2s 2p electrons we grouped together. 2s 2p, how much electrons there? 6 plus 2, 8 electrons there. Okay, and 3s and 3p, how much electrons here? 3 electrons. Okay, and then according to Slater's rule, what is about the third step? We have to select, we have to choose which group electrons we are going to calculate the effective nuclear charge for the which group electrons. Okay, so we know what is the question. Our question now, calculate the effective nuclear charge on a 3p electron. So this 3p electron effective nuclear charge you are going to calculate. Okay, 3p means the s and p orbital grouped together. So we want to grouped together for s and p orbital. So totally 3 electrons is there in p orbital. Okay, so there is we given the name. There is nth last orbit. Which group we chosen? That group we given the name n, last orbit, nth orbit. Okay, before that n minus 1, and before that n minus 2. Okay, already we know what is the formula for calculating effective nuclear charge? Z EFF is equal to Z minus S. Z means atomic number, S means screening constant. It's the screening constant. First upon we have to calculate the screening constant for each electron for this group. Okay, for that they given certain the constant value for S. Okay, constant value given for the nth orbit. If you are calculating S and P orbital, what is the nth orbit value? 0.35 for the all electron in the nth group. Okay, and n minus 1 group, what is the value? 0.85. If you are calculating S and P or group elements, we are calculating S and P group elements, electrons. What is the n minus 1 value? 0.85. And n minus 2 and others lower inertials, what is the value? 1. Okay, D and F for the nth or nth group 0.35, n minus 1 group, what is the value? N minus 1 and other lower group, all groups 1. Okay, what is the value? 1. Understood? So here the group name N, group name N, how much electron, number of electrons in this group, how much electron for the nth group? Totally 3 electrons, but as already I told you, for the nth group if we are taking the electrons from the nth group, we should subtract from total number of electrons with 1. Okay, we have to subtract 1 from this nth group electrons. Okay, so 3, total number of electrons 3 minus 1 2. Okay, so how much electrons in nth group? 2 electrons. After that, what is the given S value for the nth group? For S and P or groups, that is 0.35. And n minus 1 group, how many electrons? N minus 1 group, how many electrons are there? 8 electrons. 8. What is the value given? 0.85. Understood? And all other n minus 2 and all other inertials, what is the value? 1. Okay, total number of electrons here 2. So value 1. Understood? I should multiply the total number of electrons and n value. Here particular groups, nth group for the S value 2 into 0.5, 0.7, and for the n minus 1 group 8 into 0.85 we get 6.8, and 2 into 1 we get 2. Okay, by adding these 3 values 9.5 we get 9.5. So what is the effective nuclear charge? How will you calculate? What is the formula? ZEFF is equal to Z minus S. Okay, here Z means atomic number, aluminum atomic number 13. We know 13 minus, what is the S value? 9.5. So we get, what is the final value? 3.5. Understood? These are about the calculation of effective nuclear charge on the 3p electron in the aluminum atom, and the chlorine atom also having, you should practice how to calculate the effective nuclear charge on the 3p electron in chlorine atom. Okay, this try to practice. Okay, students, now we move to our today's class. Today our class means variation of atomic radius in group. Okay, in last class we studied about that variation of atomic radius in periods. Okay, when we are moving from left to right, the atomic radius decrease. We learned clearly about that. Today, how the atomic radius varies in a group. Okay, so when we are moving from top to bottom in the periodic table, top to bottom, that is in group, top to bottom, there are how much groups are there? 18 groups are there. Each period, each group, how the atomic radius varied. Okay, that is now we are going to study. Okay, so here let's see here, this is the first group: hydrogen, lithium, sodium, potassium, rubidium, cesium. This is the first period elements. Okay, the first period element, you see the atomic radius. The atomic radius increase. How the atomic radius increase? Because the number of atomic number increased. Okay, hydrogen atomic number 1, lithium 3, sodium 11, potassium 19. Okay, when we are moving from top to bottom, atomic number increases for all the elements. Atomic number increases. When atomic number increases, nuclear charge also increases. Nuclear charge also increases. When nuclear charge increases, the number of when we are moving from top to bottom, number of shells also increases. Okay, for hydrogen atom, first this is the nucleus, only one shell having. Okay, for the lithium atom, only two shells having. First shell 2 electron, second shell 1 electron. For sodium atom, how much? 3 shells. For potassium atom, totally 4 shells. Rubidium, 5 shells. Okay, so when we are moving from top to bottom, the number of shells also increases. Okay, so here atomic number increases, number of proton increases, nuclear charge increases, but number of shells also increases. So over y the increase in nuclear charge, the number of shells also increases successfully, so it override the nuclear charge. Understood? So when number of shells increases, the distance between the outermost shell and nucleus increases. The distance also increases. Understood? When distance increases, the electrons are loosely bound, so the screening effect also takes place here. The inertial electron acts as the screen. Okay, the inertial electron repel to each other. So nuclear force is less here. Okay, nuclear force is less. Okay, understood? So because of this, the atomic size increases. Okay, but when we are moving from left to right in a period, the atomic number increases, number of shells, the same shells. Okay, so the screening effect less there. Screening effect is less. Okay, so the electrons, the nucleus, the protons is tightly attracts the electrons towards itself. That's why the atomic size decrease. Okay, but here when we are moving from top to bottom, here inertial electrons repel each other, so the nuclear force from the nucleus and outermost electron is low. Nuclear force is low, so the atomic size is increased. Understood? These are about the periodic property about in group. Okay, so this is that periodic table. When we are moving from left to right, the atomic size is decreased. When we are moving from top to bottom, atomic size increase. Okay, understood? These are about this is the one of the graph shows. This is the variation of atomic radius or covalent radius of the group 1 element, that is lithium, sodium, potassium, rubidium. Okay, so when we are moving from top to bottom, atomic radius increases. Okay, this is another one graph. This is the third period elements, variation of atomic radius in period. Okay, so the when we are moving from left to right, atomic radius decrease gradually. Understood? These are about the atomic radius. Okay, then we are going to study about ionic radius and how to calculate the ionic radius for the different ions. Okay, what do you mean by ionic radius? Ionic radius means it is defined as the distance from the center of the nucleus of the ion up to the outermost electron cloud. Okay, what do you mean by ionic radius? It is defined as the distance from the center of the nucleus of the ion up to which it exerts its influence, on the electron cloud of the ion. Understood? So ionic radius means a distance between the center of the nucleus of the ion up to which it exerts its influence on the electron cloud. That is called ion. Okay, what do you mean by ion? Let us discuss with an example. What do you mean by ion? When an atom it is in neutral state, does not exist in freely except noble gases. Noble gases only stable electronic configuration, it exists in free state, but all the other atom does not exist in free state. We know that is for example sodium. I am taking the sodium ion, atomic number 11. So here nucleus, what is the electronic configuration? 2, 8, 1. The first shell, how much electrons? 2 electrons. Second shell, 8 electrons. Third shell, 1 electron. Understood? So it does not does not exist in free state because outermost electron only 1 electron having. Okay, so it always try to remove this 1 electron to attain the stable octet configuration. We know about that. So when it remove the 1 electron, it lost 1 electron, it becomes ion. Okay, the sodium atom, when it remove or lost the 1 electron from its valence shell, it becomes sodium ion, Na plus. Suppose it remove 2 electrons from the outermost shell, that is Na2 plus. Okay, but sodium atom only can remove only 1 electron only. Okay, when it remove this 1 electron, it gets stable configuration. Okay, students. So sodium, it lost 1 electron from its outermost shell, and it becomes sodium ion. Okay, like that fluorine. I am taking fluorine. What is the atomic number for fluorine? Fluorine 9. Fluorine 9. What is the electronic configuration? 1s2, 2s2. There is a shell. How much electrons? It arranged in a shell. Atomic number 9, 2, 7. Okay, 2, 7. First orbit, 2 electrons. Second orbit, how much electron? 7 electrons there. Okay, it is not in free state because total how much electrons are having? Only 7 electrons are having. Okay, so the fluorine atom need 1 electron to get the stable configuration. Okay, when sodium atom remove 1 electron from its outermost electron, this fluorine, it accept this 1 electron, it gain this 1 electron to form fluoride ion. Fluoride ion. Understood? So ionic radius, what do you mean by ionic radius? Ionic radius, it is defined as the distance from the center of the nucleus of the ion and it up to which exert its influence on the electron cloud of the ion. Wherever the electron cloud takes place, there is that distance. There is called the center from the center of the nucleus and the outer shell electrons. That is called ionic radius. Okay, ionic radius of univalent crystal. Univalent means only one valent. Only one valent. What do you mean by valency? Valency means, you know, valency means how many electrons one of the atom, how much electrons can lose or can gain. That is the valency. Okay, for the sodium atom, how much valency? Only one valency because it can lose only 1 electron. So the valency of sodium atom 1. Okay, so the ionic radius of univalent crystal can be calculated using Pauling method. One of the method here, that is which method? For Pauling method. Okay, Pauling's method, we can calculate ionic radius of 2 ions. Univalent crystal ions. Okay, the Pauling method from the interionic distance between the nuclei of the cation and anion. Okay, according to Pauling's method, we can calculate the ionic radius, that is the distance between the nuclei of cation and anion. Understood? When sodium atom, it lost 1 electron, that electron fluorine atom gain, and for the sodium atom and chlorine atom, one of the bond is formed, that is ionic bond. Already we studied about that. What is ionic bond? What do you mean by ionic bond? The bond is formed between the two atoms by complete transfer of valence electron from one atom to other atom. Okay, here sodium atom lost 1 electron. So that electron chlorine atom accept. Okay, here ionic bond is formed. Okay, so what is ionic radius here? The distance between the center of the nuclei of two ions. Nuclei of two ions. That is called ionic radius. Understood? So how to calculate the ionic radius? Here, according to Pauling method, here we have one of the formula, that is the D. D means distance. Okay, ionic radius, D is equal to RC plus RA minus. Okay, RC plus means, what do you mean by C plus? C plus means cation. Cation. Okay, for example, sodium atom can remove one electron from its outermost shell. So when it remove one electron to form sodium ion, positive ion or cation, sodium plus Na plus, or Na cation, sodium ion, cation. The positive charge, it is the cation. Okay, when fluorine atom, it gain one electron from the sodium atom, it form the anion, fluoride anion. The minus charge, it indicates the anion. Plus charge indicate cation, minus charge indicate anion. Understood? So according to Pauling method, how to calculate the ionic radius means D is equal to RC plus RA minus cation. When we are adding the radius of cation and radius of anion, that is called ionic radius. Understood? Where D is the distance between the center of the nucleus of cation and anion. Okay, this is the formula for calculating the radius of cation and radius of anion. But using this equation, we cannot, using this formula, we cannot correctly calculate the radius of the cation and anion, because of the radius of the cation is very smaller than the radius of the neutral atom. Okay, for example, sodium atom, atomic number 11, we know electronic configuration 2, 8, 1. First orbit 2 electrons, second orbit 8 electrons, and last orbit only 1 electron. Okay, when this is the neutral atom, when it lost this one electron to get the stable configuration, when it lost this one electron, the outermost orbit also here lost, remove. Okay, so here the electrons, the nucleus force, okay, the number of proton here higher than the number of electron. Okay, atomic number means number of proton and number of electron. Okay, here 11 number of protons are having here, but number of electrons only 10 electrons only having here. Okay, so the number of protons is low means the nuclear charge higher than the electrons. Okay, so the nucleus, it can attract very high force with the nucleus. Okay, when it attracts the nucleus electrons very high force, the size of the radius of the cation will be low. Understood? Okay, in the case of anion means fluorine, the neutral atom atomic number 9, so 2, 7. First orbit 2 electrons, second orbit 7 electrons. Okay, so it always attract 1 electron to get the stable structure. So when sodium atom remove this 1 electron, fluorine atom attract this 1 electron to get the stable configuration. Okay, here see here number of protons 9, but number of electrons 10. Understood? So the nuclear force is here very low, because the number of electrons is high here. Okay, nuclear force is low, so the size of the anion will be high than size of the neutral atom. Understood? So because of this next one more assumption given by the Pauling's method. So that is the radius of the cation, it is inversely proportional to the effective nuclear charge of the cation. Radius of the cation RC plus, it is inversely proportional, that is 1 by ZFF than the C plus, okay, inversely proportional to, because the size of the cation will be high, the radius of the cation will be low. Okay, when nucleus nuclear force, effective nuclear charge means nuclear force, effective nuclear force. The nuclear force is high means the radius will be low. Okay, the electrons attract by the nucleus very tightly, so the radius electrons will come towards the nucleus. So radius of the cation will be low. Okay, like that, radius of the anion, that is Ra minus, it is inversely proportional to the effective nuclear charge. Okay, here when effective nuclear charge is high means radius of the anion will be low. Effective nuclear charge low means radius of the anion will be high. Understood? So these are about the second assumption. By dividing these two equations, that is Rc plus by Rca minus is equal to 1 by ZEFF A by 1 by ZEFF C plus. When we are dividing, this will go here, this will come here. So Rc plus by Ra minus is equal to ZEFF A minus by ZEFF C plus. Understood? Okay. By solving this equation number 1 and equation number 4, the values of Rc plus and Ra minus can be obtained. Okay, if we know the interionic distance, that is D. Okay, if we know the D from the equation number 1, D is equal to Rc plus Ra minus. If we know the distance, interionic distance we know, we can calculate the radius of the cation and radius of the anion. Okay, here for example, let us explain this method by calculating the ionic radii of Na plus and F minus in NaF crystal. Okay, we are taking here NaF, sodium fluoride crystal, whose interionic distance is 231 picometer. Interionic distance we know for the sodium fluoride crystal, interionic distance, that is 231 picometer. Okay, so what is the first equation number 1 means? D is equal to Na plus plus Rf minus. We are taking this equation number 5. That is, we know the distance D, we know 231 picometer. Okay, so the Na plus plus Rf minus is equal to 231 picometer. This is, we take equation number 6. Okay, we know that this Rna plus by Rf minus, that is ZEFF F minus by ZEFF Na plus. Okay, by calculate the radius of the sodium and the radius of the anion, we are using this assumption, that is Rna plus plus or F minus is equal to ZEFF F minus by ZEFF Na plus. Okay, here ZEFF F minus, that is means effective nuclear charge for the fluorine atom. Effective nuclear charge for fluorine atom. What is the effective nuclear charge for fluorine means? Fluorine anion. Fluoride anion, that is, what is the electronic configuration for the fluoride anion? Atomic number for fluorine we know 9. So the electronic configuration 1s2, 2s2, 2p, 2p, 5. Okay, 2p5. But here we are calculating the effective nuclear charge for the fluoride ion. Ion means F minus. So extra 1 electron having. So the extra electron we are added to the p orbital. Okay. So we get 1s2, 2s2, 2p6. 1s2, 2s2, 2p6. Understood? So according to Slater's rule, we can grouping these electrons. First 1s2 electron and 2s and 2p electron. That is how much totally? 2 plus 6, that is 8 electrons. Okay. So when we are calculating the effective nuclear charge by Slater's concept, we are taking, this is the nth because we are going to calculate the effective nuclear charge for the screening constant for the p orbital, 2p orbital. Okay, by calculating the effective nuclear charge, what is the formula? Is that EFF is equal to Z minus S. Okay, so for fluoride ion, is that EF minus is equal to Z minus S. Okay, we have to calculate the S value here. For calculating S value, we are taking this is according to Slater's rule. The first for the last orbit, which electron we are going to calculate, that is we taken as the S, N. Before the shell, we are taken as the N minus 1. Okay, we know N, what is the N value for S and P orbital? That is 0.35. How much electrons are we having here? 8 electron. So we have to take 1 electron minus. Okay, 8 minus 1 is equal to 7 electron. N is equal to 7. So 7 into 0.35, what is the value we get? 2.45. 7 into multiplying 7 with 0.35, we get the 2.45. Okay, after that N minus 1, what is the value for N minus 1? That is 0.85. How much electrons are having in the N minus 1 group? There are 2 electrons. So 2 into 0.85, 1.7. 1.7 we get. When adding these two values, we get 4.15. This is the S value for the fluoride ion. Fluoride ion. Understood? So the when we are subtracting, what is the atomic number here? 9. 9 minus 4.15, what is the value we get? 4.85. Okay, like that we are going to calculate effective nuclear charge for the sodium atom, sodium ion, sodium cation is that EFF into Na plus. Okay, so what is the atomic number? Z minus S. Z means atomic number for sodium 11 minus, what is the S value? How will you calculate the S value? Sodium Na plus ion, effective nuclear charge for the Na plus ion is equal to screening constant. We have to calculate what is the, for calculate the screening constant, what is the electronic configuration here for sodium ion? 1s2, 2s2, 2p6. Okay, 3s electron are removed. Okay, 2p6 here. Even grouping these electrons, 1s2, 2s, 2p, 8 electrons. Okay, this is same as the fluoride ion. Okay, so we know that is 4.15 value for the p orbital. 4.15 value. So 11 minus 4.15, we get the 6.85. Okay, here what is the our equation? R Na plus by R F minus is equal to Z EFF F minus by Z EFF Na plus. What is the value for Z EFF F value? 4.85. R Na plus by R F minus is equal to 4.85 by 6.85. Okay, understood? So by dividing these values, we get 0.71. Okay, so RNA plus by RF minus, we get the 0.71. Okay, from these values we get we are taking the sodium plus ion radius. Okay, we have to calculate the sodium and fluoride ion radius we have to calculate. Okay, because of that we take the radius of cation out, so we get RNA plus is equal to 0.71 into RF minus. Okay, understood? Substituting the value of RNA plus, this is the value for RNA plus in equation number 6. Okay, equation number 6 means RNA plus plus RF minus is equal to 231 pm. So for the RNA plus we substitute these values 0.71 into RF minus plus RF minus is equal to 231 pm. Okay, so here the 0.71 RF plus RF minus. Okay, here RF minus means 1 RF, 1 here having. Okay, 1. So we are adding these two values, 0.71 plus RF minus plus 1 RF minus means 1.71 RF minus. Okay. When we are adding 0.71 plus 1 means 1.71 into RF minus. Okay. So it's equal to 2:31 p.m. So we are taking the RF minus values. So RF minus is equal to 231 divided by 1.71. 231 divided by 1.71. By dividing these two values, we get the 135.1 picometer. Okay. So here we got the value for RF minus. Okay. 135.1 picometer. Okay. Substituting the value for RF minus value of the RF minus values in equation number 6. Okay. So we get RNA plus 135.1 is equal to 231. So RNA plus is equal to RNA plus 135.1 is equal to 231. So RNA plus is equal to 231 minus 135.1. So we get 95.9 picometer. Understood? Okay, this is about the ionic radius. I hope all of you understood about the ionic radius. If you have any doubt, you can ask me. Okay. Here today we are. I give the two questions. Okay. What is ionic radius? What is ionic radius? Question number 1. What is ionic radius? And question number 2. Draw a graph. Draw a graph from the activity 3.1. That is covalent radii. The covalent radii for the third period. Third period elements. Okay. If you have book, take your book now. Students, take page number 83. What is ionic radius? Ionic radius heading for the 33 page, last paragraph. Ionic radius is defined as the distance from the center of the nucleus of the ion up to which it exerts its influence on the electron cloud of the ion. Up to here your mark. And then second question, draw a graph for the covalent radius. You take the covalent radius in the y-axis and atomic number in the x-axis and draw the graph and send me through my WhatsApp number. Atomic number, atomic number that is given in your periodic table, page number 74 periodic table. Take your periodic table. Here I have in the third period elements atomic number. Okay. You refer this atomic number. Take the atomic number in x-axis and covalent radius. This is the covalent radius. You take the covalent radius in y-axis. Okay. You draw the graph. Okay. The variation of atomic radii in periods. Understood? Thank you all of you. Thank you.